All right, so this is most likely going to be our final segment in this chapter. We've been talking about electron configurations and quantum numbers, and now we're going to start to look at some of the trends that come with it, consequences of electron configurations, and how that's going to turn into our chemical and physical properties for our elements. Now, it's very systematically with position in the periodic table, right? So where an element's position was actually based on its electron configuration. Now, remember, if we were walking through history, Mendeleev put together the periodic table based upon chemical reactivity. And then as a consequence, moving forward, we figured out the atom, particles, protons, neutrons, electrons. And then we started focusing on the electrons, looking at where the electron arrangements would lie, and 1s and 2s and all these things. So it only made sense that the electron configurations of those valence shells were very similar with the exception of the energy level, right? So in group 1A, we would notice they all end in S1. In group 2A, they all end in S2, so forth and so on. Now, to explain this then, what we must first consider is the amount of positive charge felt by the outer electrons, okay, so the valence electrons. Now the core electrons will spend most of their time closer to the nucleus. So if you think about this as a magnet with a pull in the very center, and then of course as I put electrons around that atom, it starts to diminish the way the magnet can affect the outer levels. So if I've got a sphere of charge kind of hindering that positive, if you will, then I have another shell of charge and another shell of charge. So as we move out, then the outer shell is going to feel less consequence from those core electrons being filled. So they sort of act as a shield, or they'll cancel out or screen some of that positive charge of the nucleus, right? So in other words, if I have lithium, and here I've got a +3 because we have 3 protons, but we've got 2 electrons that are filling that first shell, right? So the 1s is completely full. Well, this electron out here then would feel a net charge of about +1, but it's also further away. So we have 3 protons, we have 2 core electrons in that 1s, and we're going to get a net positive charge felt by the outer electron should be about a +1. Now it's approximately 1 proton. So what we call this is the effective nuclear charge, and we refer to it as Z sub EFF effective, right? So net positive charge of the outer electron and what it will feel. Now core electrons will shield those valence electrons from the full nuclear charge. Okay, so our topic here is going to be shielding. Electrons in the same subshell don't shield each other. So again, if we go back and look at that lithium, the 2 electrons that are in the 1s are not helping to shield each other because they fill the entire level. They together act as a shield. Okay, they're going to have the same average distance from the nucleus if they're in the same shell. So trying to stay away from each other is just as important as being attracted to the nucleus at that point. So they're going to spend very little time one below another. Okay, the effective nuclear charge then will be determined primarily by the difference between the charge on the nucleus and the charge on the core, the number of inner electrons. So the more electrons that are in the core, the more they will diminish that effective nuclear charge felt by the outside. All right, so what value is the closest estimate for Z effective for a valence electron of the calcium atom? Okay, so if we're looking at the calcium atom, we'll go to our periodic table, and we'll see calcium is number 20, so we've got 20 protons, and then we've got 18 electrons in the core, which means there's 2 protons unaccounted for, and so the valence electron, the Z effective for them will be about a 2. Okay, so Z effective then would be 20 protons minus 18 core electrons, which would equal 2. Now, atomic size. The theory suggests sizes of the atoms and ions are indistinct. Experiments show that atoms and ions behave as if they have a definite size. Okay? So carbon and hydrogen have approximately the same distance between nuclei and large numbers of compounds. Okay, now what we're going to be looking at now is atomic radius. half of the distance between two like atoms. So in other words, what we're going to do is we're going to get two hydrogen atoms, and they're going to combine to make H2. And then what we're going to do is measure the distance between the two nuclei, okay, between the protons, the nucleuses, nuclei. We can't see the electron clouds that well, but we do have plenty of ways to see protons. So protons are a little bit larger. Remember, they're an atomic, a particle size of approximately an atomic mass unit of 1. They're much heavier than the electron, so we can actually measure them. So we can see the two protons, and we can measure the distance between the two protons. So what we're going to do is we're going to take half that distance. Okay, so that's how we're going to calculate our atomic radii. So in other words, we're going to take H2 and we'll measure the distance between two hydrogens. We'll take C2, we'll measure the distance between two carbons. Now, usually we'll use units of the picometer. So 1 pm is about 1 times 10 to the negative 12 meters. Okay? And atoms will typically range between 37 and 270. Not worried about that. What I'm worried about, you all understanding, is the trends in the atomic radius. What's going to happen as we move around on the periodic table to that radius? Well, as we move down a group, the atoms get larger. The Z effective will essentially stay constant. So as I keep adding a shell, we'll still have the same number of effective charge hitting that outside electron. Now, as increases, the outer electrons are farther away from the nucleus, so the radius will actually increase. So that's how we can tell that the effective charge is actually reducing, because as we move out, the distances are getting larger, but so is that difference. Okay? Now, as we move across the periodic table, we'll see a decrease. Now here, it's going to be constant, right? So all the numbers are going to be constant. The nucleus is constant. We're adding 1 proton, and the distance is staying the same, the shell is staying the same. The effective charge then is actually going to decrease. So the outer electrons feel larger Z effective, and the radius will actually decrease. So it's a little counterintuitive. Think of it as turning up the electric on an electromagnet. If I keep turning up the charge, adding more protons to the center, the overall effective charge is actually going to bring those electrons in closer, making the atom appear smaller. Now for transition metals and intertransition metals, the size variations are less pronounced as filling in the core. Okay, remember you're in the same shell still, but your Z effective is going to decrease, and that's going to affect the radius a little bit more gradually. Take a look at the periodic table here, and we can see some of these charges. All right, so I can't really see these numbers. I apologize. So here we have a hydrogen at 37. We see helium at 40. They're about the same. Yeah, I'm having trouble seeing the numbers, but you can see the overall. This is what I really want you to know overall anyway. I'll give you the numbers if you need them. As we move across the periodic table, we see that the size is going to decrease. And of course, as we move down the periodic table, we're going to see the size will increase. Right? So as I move across, it's getting smaller because that Z effective is getting larger and pulling those electrons in closer. And if I move down the group, then I'm actually adding a shell, and so we're going to see an increase in atomic radii. All right, so ionic radii. Now things are going to play a little different. So here we're going to look at fluorine versus fluoride. So fluorine has a measurement of about 128, but if I add an electron, now I have the same effective charge, but I have an extra electron that I have to pull on, which means what I'm going to see is a decrease in that effective charge. And so fluorine is going to get larger. Now for lithium, we see it 304, but it becomes a +1 ion, and we see it shrinks. All right? And that's because, again, the Z effective charge is going to stay the same. But if I take an electron away, then that's 1 less electron that's going to feel that overall charge, which is going to pull everything in closer. Okay? Here's a nice little example with iron. Iron is 232. We get rid of 2 electrons. We see it drop to 152. We get rid of a 3rd electron, and it drops again. Okay? So the effective charge is staying the same, but the electrons are diminishing. And so that overall effective charge, each electron that's still there is experiencing a greater pull. So it's going to increase as we go down the column. It's going to decrease as we go across the period. For anions, they get larger than their parent, and that's always going to be a guarantee. Okay, anions will always get larger than the parent atom. And again, that's because you have the same effective charge, but now we have more electrons that the effective charge has to tend to, if you want to think of it that way. The radius will always expand. Cations always are going to be smaller than their parent atom. The effective charge, same, but now we're dealing with less electrons, which means the electrons that are there are experiencing a greater charge. The radius then will contract. All right, so your turn. Which of the following has the smallest radius? Now again, you're going to want to grab your periodic table and think about these trends. So if I look at the periodic table, let's see, do a quick drawing here. All right, that's supposed to be my S group. Not the greatest, but you know, it's going to get the job done for us. There's my little stinky helium up there. All right, so here we're going to be looking at argon. So again, just a rough sketch. Here's argon right there. So there's Ar. Then we have potassium plus. So here's potassium. Then we have chloride, chloride minus. So chloride minus would be here. Okay, then we have calcium 2 plus. And then last but not least, we have sulfur 2 minus. All right, we want to know which one is the smallest. All right, well, we know it's going to get smaller as we go this way. We know it gets larger as it goes this way. So right away, if all things were the same, potassium would be the biggest, argon would be the smallest, right? But they're not all the same. We have two ions here, -2 and -1. Well, we just said that if we have an anion, they get larger. So they were already not the smallest. Now they're going to be even larger, so we know they're out. And then we have the calcium. Now the calcium is going to decrease by a +2. So now, without having numbers, really, you're down to 50-50, right? Argon or calcium 2 plus. Now remember, it does get smaller as I go this way. So even though I've added a shell, I'm only one in, but I'm going to take both of those electrons away. So the effective nuclear charge would be greater here than it is here. But I have less electrons to tend to over here. So I believe the answer is going to be D, calcium 2 plus. All right, let's see how you do with this one. Arrange the following from smallest to largest. So we want the smallest to largest radius. Okay, so what's going to be smaller? So again, if we think about our periodic table, we know oxygen is going to sit here. We know sulfur is going to sit here. We know it gets larger as we go this way. And we want to get smallest to largest. Now we know if we make a negative charge, it's going to get larger. And so one of the ones we're going to contend with is sulfur 2 minus. So it's at the bottom and it's got a -2. So we know S minus 2 is going to be the largest. So we can eliminate that one and that one. Then after that, we have O2 minus, but we also have an O2 plus. So we have oxygen, O2 minus, O2 plus. So, well, in these three, we know this would be smallest to largest, right? So smallest to largest. It would just be a matter of, do we think the O2 minus would be larger than the S2 minus? And S isn't even in this, so we don't have to worry about the S. So S2 minus would definitely be larger than O2 minus because it's the same charges, but remember as we move down it gets a bigger shell. So that means we're going to want O2 minus next, so I'm guessing the answer is going to be C. And there it is. All right, the next trend we want to look at is ionization energy. Ionization energy is the energy required to remove electrons from a gaseous phase atom. This corresponds to taking an electron from n to n equaling infinity. So we want to make it go from n to n equaling an infinity. So first ionization energy, for instance, I take a metal, put it in a gaseous state, I pull an electron out, and now I have m plus 1 plus an electron. The IE here would be equal to the delta E. IE is equal to the Rydberg constant times the Planck's constant times the speed of light times the Z effective squared divided by the shell number squared, the energy level squared. So all of that just to say what are the trends? Well, they're the opposite of the size. Ionization energy decreases as we move down a period or down a group. So as the atom adds a shell, right, it's getting easier and easier to pull an electron out. And you think about it, what's holding the electrons in is the nucleus. So if I move the electrons further and further away from the nucleus, it's going to be easier to pull them out. Ionization energy will increase as we move across the row. Now that makes sense as well, right? Because we saw that the electron was getting smaller, the atom was getting smaller as I moved across the periodic table because the electrons were being pulled in closer. If they're being pulled in closer, it's going to be harder to pull one out. That means the ionization energy is going to go up. So ionization energy is how much energy it's requiring me to pull an electron out of the atom. The further away from the nucleus the electron is, the easier it's going to be to pull out. If you compare your first ionization energies, it's going to look just the opposite as the size. Largest first ionization energies are always in the upper right corner, okay, and the smallest ones are down in the lower left corner. Now, we can also look at successive ionization energies. Obviously, we know some atoms want to lose 2 and even 3 electrons. So when we do that, it's going to increase slowly as we remove each successive electron. So the first one will be difficult to pull out. The second one's going to be a little more difficult to pull out. Now, obviously, when we hit different parts, we're going to see a decrease. For instance, calcium. To pull 1 electron out of calcium is going to be difficult. To get the second one's not going to be a problem at all. It's going to be happy to give it to me. Right? But overall, it's still going to cost me more energy to get to +2 than it does to +1. Okay. So again, if I'm looking at successive ionization energies, obviously hydrogen only has 1 electron. Helium, to pull the first one is expensive. To pull the second one's even more expensive. For lithium, to pull the first one, not so bad. Remember, lithium wants to lose the electron. To get the second and the third one, though, it's through the roof. Beryllium, again, not too bad to get the first one, not too bad even to get the second one. But then the third and the fourth, again, it's going crazy. Now remember, this line is marking our 1s2, right? So all of these would be the 1s2 electrons. Down here, we're looking at sodium, we're going to see a repeat, right? Remember that electron's getting further away. So if I'm comparing lithium with sodium, it should make sense. It's easier to pull an electron out of sodium than it is lithium. To pull the second one, again, a little easier. It's further away. Okay, pull the third one, should be a little lower again. All right, so write the chemical equation that corresponds to the second ionization energy of potassium. So remember, we want to pull the second electron out of potassium. That means we have to be starting with K plus, right? Also, we know we're doing this in gas, which means our answer has to be D. Place the elements carbon, nitrogen, and oxygen in order of increasing ionization energy. So increasing ionization energy. So whenever people get confused with ionization energy, what I always tell them to do is think about atomic size. Place the elements carbon, nitrogen, and oxygen in order of decreasing atomic size. So decreasing atomic size, right? So we want the big one first or the small one first? We want decreasing, so we're going to want the biggest one first. Okay, so first then we'll have C then N, then O. That would be the size order, right? Now, increasing ionization energy. So what are we thinking here? Is it going to be the same, or is there going to be any changes? All right, good. So I would expect you to have picked A. The textbook, however, is telling us it's going to be C. And I don't know why they've got oxygen in front of nitrogen there for ionization energy. It should be easier, right? It should be more difficult to pull an electron from carbon, then nitrogen, then oxygen. But they're saying it's this way. I would say it's going to be A, though. That's what I would expect on an exam. Arrange the following from highest ionization energy to the lowest. And again, think about size here. Arrange the following from the highest ionization energy, smallest atomic size, to largest. So if I want to go from small to large. All right, so which atom would be the smallest? Of course, that'd be O2 plus, right? Then it would be O, then O2 minus, then S2 minus, and that would be C. All right, electron affinity. Now, potential energy change associated with addition of one electron to a gas phase atom. So now, instead of taking an electron out, I'm going to put an electron in. And of course, we know our anions will like that, right? So chlorine is going to accept that electron. Calcium, on the other hand, no bueno, does not want to accept that. So, but that's what we're going to look at. Now we're going to look at how much energy does it cost to push an electron in. So oxygen and fluorine, very favorable to add electrons. They actually like it. Comparing the first electron affinities usually is negative exothermic. So for some of these atoms, we're going to see it's going to actually give off energy in order to accept the electron. The larger negative value means a more favorable to add an electron. So here we see hydrogen accepting an electron is negative 73. Lithium, negative 60. Beryllium doesn't want to do it, plus 238. All right, fluorine, negative 328. It's giving us a lot of energy to get that electron. Chlorine's giving even more, 349. All right, so your trends in electron affinity pretty much follow ionization energy. So the EA will increase as it goes across. Now the opposite part here is it's going to increase as it comes up, right? So electron affinity becomes less exothermic down the column as the shell increases. Okay? Electron affinity becomes more exothermic across the row. So it's easier to attract electrons as positive charge increases. So as the atoms get larger, it's easier to attract the electrons. For successive electron affinities, the addition of the first electron is often exothermic. Addition of more than one electron usually requires energy, so we'll go back to being positive. Consider the addition of electrons to oxygen. The first one, we get a negative value. The second one is actually a positive value. So the overall then would just be simply summing these up, and we saw that when we looked at Hess's law and delta H's of reaction. All right, so write the chemical equation that corresponds to the electron affinity of germanium. So we're going to take germanium, we're going to add one electron. Again, we have to be in the gaseous state. So of course that's going to be D. All right, going a little long here, but we only have a couple slides left. Which of the following has the largest electron affinity? All right, this is going to be a no-brainer. The one that always wants all the electrons is going to be F. Even though the values showed chlorine being a little higher, fluorine is always your go-to. So whenever we're looking at electron affinity, who wants the electron the most, it's always going to be fluorine. You're always going to be safe feeling with that answer. Which of the following has the smallest electron affinity? And out of these, it's going to be phosphorus. And again, you might want to draw out a periodic table real quick, or just grab your periodic table, look at where they are. Don't worry about too much about numbers. What we're going to be looking at is trends here. Okay, so don't spend a lot of time with numbers. Just think about how the periodic table works as trends. All right, that's going to conclude our quantum atom. And so we'll move on from here. I believe our next topic, if I recall, is gases. Let's see, is that right? Oh, that's the wrong. See, after our quantum atom, we have, oh, nope, it's going to be the basics of chemical bonding. So chapter 8 will be the basics of chemical bonding. So we'll probably start that out with stuff that you're probably familiar with if you've had a 110 or a general chem in high school. So, but that will conclude all of our nuclear talk. So if you have questions, make sure you get a hold of me. If not, stay tuned until the next chapter.